Good morning. All right, so today we are going to talk about GloVe. What is the date today? 20? No, 30. Okay, so today we are going to talk about GloVe, and the title of the paper is So today we are going to talk about the GloVe, global vectors for word representation. Our topic still remains the same. It is for the, we want to learn good representation of words, and the authors are Jeffrey Pennington, Richard Schocher, and Christopher Manning. Okay, so I am just writing his name in short form. This is, so these people are from NLP group at Stanford. So today we are going to talk about this. Now, any questions about word2vec? Any comments about word2vec? What was good, bad with it? Unless you go revise what we have done, trust me, all will evaporate from here. Okay. All right, so we start now. So in this particular paper, what authors say is, so they kind of build on the idea of, they make word2vec much simpler. Okay. So what was the idea behind word2vec? What was the core idea behind word2vec? Yes? We want to learn word vectors, but what was it? What do we want to learn in word2vec? Tell me, what do we want to learn in word2vec? Second question is, what is our training process doing? We have had 5 lectures on word2vec.
What comes after the word in the corpus? Like what if it is?
So, which words are in that window? Context and center word window. Okay. What does that tell us? So, what was our training objective there? Okay, let me rephrase my question. What was our training example there? Like if you want to recognize, if you want to make a object detection cat recognizer, you are given an image and you are also given label whether there is cat in this or not, and then you train on such examples. So this is an example of one training data set, right? My question here is, what is the example of a training data set in case of GloVe? What is the example of a training data set in case of GloVe? One example. Guys, one example was this pair. Remember, we had an input word, we had a output word. So one example was pair. So what are you training? You are training the system to learn that this particular word comes in context of center word. Okay, so this is my context word, this is my center word. We are trying to figure out what are the context words when this particular word is the center word. This is our training that we are doing. But do we really want to be good at this task? What are we eventually doing? Do we want to be good at this task? So at the end of the day, are you going to ask this question to your machine learning algorithm that, see, given this center word, what is my context word? Are we doing that? So why are we learning all these things? Your training objective was, what is it that we are training on? See, if you want to build a cat recognizer, what are you building? Given an image, you are given a label. And you are running this on training examples, and finally what will be your test data? Again an image, and on which you will say either yes or no, depending on whether there is cat or no cat. In this case, what are we training on? What is our training data? Center word, comma, context word. So we have trained on billions of such examples. So during test time, what are we going to do? Are we going to ask this question that given this word, tell me what is the context word? Did we ever ask this question? No. Then what is it that we are trying to do? We are more interested in those 300 numbers for every word. Okay? So we are interested in these numbers here, these matrices here. So word2vec is one of the very classic examples of this thing, that you are training on a dummy training example. What is that dummy training data set? See, the beauty of this paper lies in this fact that you have huge corpus, everything unlabeled, okay, but still they were able to figure out of a task. You complete that task and you will end up learning good word embeddings. This is the beauty of that paper. What is the training example? What is the training procedure that you are taking? Given center word, what is the context word? And keep on predicting these things. You do it for billions of pairs. Alongside what is happening, you are more interested in that. So what are we more interested in? We are more interested in these weight matrices. We are going to take these 300 numbers for every word. If doing this side task, it helps us learn good word embeddings. This is what word2vec paper has shown. Any questions on this? See, until now, no matter which kind of learning algorithm we saw, for example, that housing price prediction, what did we do? What was the training example? What was the test example? Training example was the features related to house and then price. So you have lots of such example. What are you going to test on? Similar features and then your price on that. Cat recognizer. If you are building a sentiment classification application, what will you do there? So text and then sentiment, whether good, bad, neutral, whatever. Okay? And what are you going to test it on? Text and then again whether it is good or bad. When you are doing translation, you are given a corpus in English, you want to translate it into Hindi. You are given this parallel corpus, and what are you going to test on? A new data set that again you want to translate from English to Hindi. So until now, whichever algorithm we had seen, it had this one property: your training data set is going to be used directly as in your test data set, in the sense that the task on which you trained your algorithm is going to remain same for training and test. In this case, what is our main motive of learning these weight vectors? What are our motive of learning these weight matrices here? We want to learn good word embeddings, and we don't care whether our system, it became very good at predicting, given this center word, what is the context word. We don't care whether our system got better or worse on this task itself. This task itself we are never going to ask to our system. Does this line make sense? I see blank faces. See, what was the example here? One training example. What is the example? Fox, comma, quick. Okay? And then we had fox, comma, brown, and so on. So if your training examples are these pairs, generally what will we test on? Now give me a different center word, and I am going to tell you what are the context words, because this is what we trained on, right? But word2vec does not do this. Word2vec's objective is to learn word embeddings, and their training of this kind is to do something else. And they show that even though you are training for some other task, you can call it side task, fake task as people call it, right? Your actual task is to learn word embeddings. Otherwise you think it becomes so damn difficult. How are you going to do this in an unsupervised manner? Was this done in an unsupervised manner? Word2vec, whatever we did in last 5 lectures, was it supervised or unsupervised? Why supervised? Because you had an input and you had a corresponding output, so it was supervised. So that task was supervised. But what you wanted to learn? Word embeddings. So did you have supervised things for word embeddings? Like given word, this is what I have word embeddings. So was it a supervised task for learning word embeddings? No. It was supervised for guessing center and context pair, but it was not supervised for given a word, what is the word embedding. Okay? So this was kind of one of the first algorithms that did things on what we today call as semi-supervised machine learning. Okay? Otherwise you see, I mean, the beauty here lies, you have a corpus of 1 billion words, and in that 1 billion words, what are you doing? You are trying to make your training data set such that it is going to give you good word embeddings. This is a lot of hard work, because all you have is intuition. Until now, I mean before ML, whichever course on computer science you have done, it has this property. So if you are talking about an algorithm, you don't really need to step out of your table and chair. Sit there, start doing everything analytically, and you will be either able to prove something or you will be able to disprove something. In machine learning, it does not work this way. So looking something theoretically, you can't really figure out what is going on. You have to go, write code, test it on millions or billions of examples, and then finally you will be able to figure out whether it works or not. So if you have this question, why should this work? That's a genuine question. Why should this work? Right? In theory, how would you answer that? You'll prove or disprove something. In machine learning, how do you answer that? By actually going, training, and then finally showing that, see, it works. And if the theory behind that is bogus, we don't care, as long as our machine learning algorithm generalizes well. Okay. So now we are going to talk about GloVe again. So of that same era, but kind of a few months later than Word2Vec. Okay. Again, these are the authors and they are at Stanford. So what happens in GloVe? Again, what was our example? Yes. What are we going to do in GloVe now? So at a high level, what was the training, what was the objective or objective function in Word2Vec? No, what was the objective function? That mathematical equation. So we were supposed to minimize summation over I equal to 1 to t, and then for the context window, and then we were computing log of probability of, right. So probability of w plus, no, probability of w t plus j given w of t. Okay, so this was our objective function. In this case, what authors show is that your objective function can actually be very, very simple. What was the first objective we ever saw in any machine learning course? What was the first objective we ever saw in any machine learning course at this university? Huh? Mean squared error while doing linear regression, that was the first thing we saw. So we are going to get something very close to that. Okay. So you don't really need this whole summations that has a softmax, a big way softmax sitting inside every iteration, every example. So again, I'll be doing everything in to the best of my knowledge. Now, this was, so in GloVe, what you first do is, you try to make a co-occurrence matrix. So how do you compute word-to-word co-occurrence matrix? What you are going to do is, the quick brown fox jumps over the lazy dog. Actually, that's not a good example. So tell me one more thing, one more sentence about the same thing here. What should I write? One more sentence that has most of these, I mean, these words. Huh? The fox, no.
Fox is dead.
The fox is? Or maybe what I'll do is, yes. No, what I'll do is I'll use my original example. So my example is I enjoy flying, I like NLP, and then I like deep learning. Okay, so this is our corpus right now, and we want to make a word-to-word, word-word co-occurrence matrix. So word-word co-occurrence matrix is basically mod V cross mod V matrix. Okay, so this is a mod V cross mod V matrix, and for the time being we'll assume this is our corpus. So what is my vocabulary? What are the words in my vocabulary? I enjoy flying, like NLP, deep learning. So everybody knows what is the corpus is different from vocabulary, because in vocabulary every word will occur only once, okay, which was there in my corpus. So I, what was the next? Enjoy. So okay, I'll just keep it. I like, enjoy, deep learning, हाँ the right way should have been to do it alphabetically. So this is mod V cross mod V. Okay, and similarly you will have I like, enjoy, deep learning, NLP, flying dot. Now what we are going to do here is take a window of size take a window of size 1. So that window, what we mean by window in this case also is same as what we maintain word2vec. Okay, so window size is 1. So who appears in the context of this I? Enjoy. Okay, so what I am going to do here is I will put a 1 here, because I and enjoy actually form the context and center pair. Okay, so right now I am taking window size to be equal to 1, not 4, not 2, just 1. That means if I am the center word, the only two pair will be the one in the left and the one in the right. Okay, now next, so I, now who else comes in the window of I? Like, and how many times? So like comes 2 times. Okay. Any other thing? Deep, window size is just 1. So does deep come? No. Now if window size were 2, then deep will be 1 here. Okay. So 0, 0, 0, 0 and 0. What about I? This will almost never happen for any word, almost never. Okay, in which case it can occur? Okay. So now, can you do it for like?
Yes.
So I. So what will be the value here? 2. Why 2 again? Like occurs 2 times and now next like with like is 0. Like with enjoy 0. Like with deep 1. Like with learning 0. I like NLP. I enjoy flying, so this one and this one, right? Yes. And similarly you can keep on making this. I'll just complete this. Okay, and you guys can check whether this is correct or not. I am just completing it. Just a second. Yes. So is this correct? Make sure. Yes, this is full stop. What are the properties of this matrix? Is it a symmetric matrix? What is a symmetric matrix? So x equal to x transpose, that's a symmetric matrix. Is it symmetric? Is it supposed to be symmetric? Why? Because for every center word you are taking equal number of words this side and equal number of words this side. Okay? But if you change, if you alter this, let's say if you are just telling me that my window is center word and 2 words right to it, then will it be symmetric? No. Okay? So, yes. No, but this is full stop. That's also a token. Okay? Yes. Right. Yes. Right. That's right. So that should go this side too. But right. So what do I do? What changes do I make? but I won't do this now. Okay, I mean, yes, you are right. You are right that dot should have been here. So where will be the changes? Corresponding to I and dot के अलावा और कहीं पे है क्या? So only these two dots are creating problem. This is fine, right? So only these two are creating problem, dot and I. So there will be some changes here. So this will be 1, right? No, but let me make sure I am doing it correct. So this will be 2 and we will have a 2 here as well, right? Is that right or anything else? No, this last dot, okay, not with flying. This is flying, this is NLP. I could have dropped this dot, you know. All right, so done with this. Now, what do you do with these things? We are using that same window thing for computing this. How many passes do you need over your whole data set to be able to compute this matrix? So if you have a, let's say in your real corpus, you have a vocabulary size of 100k. What will be the size of this matrix? 100k cross 100k. And do you see that this will be sparse? Will this matrix be sparse? Because most of the, I mean, right. So maybe in a row you have 1000 non-zero numbers, something like that, and rest 99% will be not in context. Okay. So what was the limitations of word2vec? Limitations of word2vec was this, that you had a very local view of the data set. I have 1 billion long corpus, but when I am talking about this center word, I am talking about only this center word and the corresponding context word. Am I looking at everything else that I have had? No. What GloVe says is, it says you make this matrix kind of thing first. Okay. How is it different from what we were doing in word2vec? Center word and context words. In this case, you are saying I am summing up all the. So let's say how many examples we had in our example of word2vec when we said there are 1 billion words in my corpus and the window size is 2. How many examples were there? 4 billion. So out of those 4 billions, how are you going to make this now? So if a pair appears 1000 times, what will be the entry here? 1000 or 2000? Because fine, you will have 1000 at 2, so 2000 entries, but 1000 or 2000? See, if one pair occurs 1000 times, you will also have pairs where they are flipped. Okay, so maybe 2000 times. So what word2vec was giving you was a very local picture of what is going on in that particular window. What GloVe is trying to capture is what is going on in the whole data set. So what kind of words for which you will have high numbers here? I mean in a English corpus, not this one. So you will have a lot of populations with the, all these stop words, the, of, an, a, from, for, and so on. Okay. So local windows capture word similarity. Now in this case, what we have is, we have a global view. This is one of the differences. Word2vec was very local. It was just sitting at the center word, looking two words or whatever, k words this side and k words this side. This is giving you a global view of your data set. Okay. So now you want to find some kind of probabilities. Okay. So let me try to take it from the paper itself. So this X is our co-occurrence matrix. Okay. Now what is Xij in this matrix? So there is an entry in this matrix corresponding to, so we are talking about ith row and jth column. So Xij is basically nothing but number of times word j occurs in the context of word I. And the way we are making our windows, Xij will be equal to X of Ji. Okay. Now let Xi be, so let me write it somewhere else. They define Xi equal to summation Xik. Okay. So let Xi be equal to summation Xik. What will this summation over be? So when I say summation Xik, what are we trying to sum actually? So X sum of rows, right? Since you are, this is your, so column is your variable, you are summing over k, right? So you are summing over k. You are summing over k. K goes from 1 to mod v. Okay. So k goes from 1 to mod v. So let Xi be the number of times any word appears in the context of word I. If this summation is huge, what does it mean? The word has a lot of occurrences in the corpus. But if this summation is very low for a number, then that word is a rare word in my corpus. And if my corpus is huge, then what I can reasonably conclude is that word is a rare word in, I mean it's a rarely used word in the English itself. Okay. So what we define next, is Pij P of. This is important. Be the probability that word j appears in the context of word I. So what is Pij? Probability that word j occurs in the context of I. So how can you get this number from co-occurrence matrix? How do you get that? And guys, one reason why I am doing all these things in so much great detail is this, that we should be able to see how people think when they design new algorithms. Okay, I mean, word2vec, excellent algorithm, gives you really good answers. If I ask you to come up with another algorithm to learn word embeddings, what can you think of? This algorithm does exactly that same thing, learns word embeddings, but the approach, at least we will find until we finally go and reconcile both, that the approach are different, but they try to actually do the same thing. So what is this probability? What is this number? I mean, I am interested in this because we are going to use these things in this particular discussion a lot. What is P of ij? J given I. So if I ask you what is P of, if I ask you what is P of learning given I, what is P of what is P of I, what is P of I given like? Two by 5, right? So all you are supposed to do is take xij from here and divide it by the sum of the row. Okay, and what is that giving me? Probability that like occurs in the context of I. This is how they are defining this P of ij. Now we can question this. How does it make sense? Right? Because we are all, until now the way we have done things, we are all interested in theory. The moment somebody defines something, we want to have a theoretical interpretation of it. Now in this case, what we are saying is, have patience, because those guys who did it, how did they show that it makes sense? Do everything that you are trying to do. Finally, learn word embeddings, compare the word embeddings that you have learnt with the word2vec ones, and they make sense. So if they make sense, then only you can say everything else that you have done before this point that makes sense. Whether in theory that makes sense or not, we are not really concerned about that. Ideally it should make sense, but even if it does not make sense, but your algorithm generalizes well, this is what our goal is. So probability ij is this. This is how we are defining it. Okay. All right, now we are going to compute. So we are going to do this quickly. Again, this table comes from the GloVe paper, so you can go and have a look at that. Now again, since this comes from data, let me populate this as well for you. What are these numbers and how do they make sense at all, if at all? So this is probability of word K given ice, this is probability of word K given steam, this is probability of word K given ice divided by probability of K given steam. So basically ratio of these two numbers. Okay, we will fill that ratio. Where are these numbers coming from? So they are very specific to the corpus that the authors had. Will they be same if we try to train this on a different corpus? No, these numbers will be different. So tell me, where is this thing coming from? This P of K given ice. Which row? So this is probability of J given I. Am I right? Probability of J given I, right? So what is I? So I is ice. So which row I am talking about? Row of ice? Okay. And then K word can be any word out of the whole vocabulary set including ice. K can go from everything starting from the first word to last word in my vocabulary and including ice. So now what they are saying in this table, that we have chosen, so there could have been how many candidates for this? Mod V. But authors are saying we are choosing K equal to solid, K equal to gas, K equal to water and K equal to fashion. Okay. Now don't look at these numbers. Tell me, what do you think is the probability of K where K is solid? So what is the probability of solid? What is the probability of word solid given ice? So what does this, what does it mean to say probability of solid given ice? No, so what does it mean to say probability of solid given ice? Exactly, right? So what is the probability of solid given ice? We are talking about whether they ever occurred in the window. Okay. When, what was the center word? Whichever. Right, right. When ice was the center. Okay. So whether this occurred. What does this probability mean? Xij. So what is x of ice comma steam divided by x of ice. Now what is x of ice? Summation of the whole row. So that number gives you this one, and similarly all these things. So these probabilities, as I said, are very specific to the corpus. Again, so I come back to my question. What do you expect this probability? Probability of solid given ice compared to, so what will be the probability of solid given ice? Whatever. What is the probability of gas given ice? not very less, but at least comparatively I can say lesser. What is the probability of water given ice? From this data set we see it is higher. What about probability of fashion given ice? Low. Okay. Now how do I interpret these numbers? Can I make sense of these numbers per se? Not really. Okay. So same here. What is probability of solid given steam? Low. What is the probability of gas given steam? Relatively higher. What is the probability of water given steam? Again high. What is the probability of fashion given steam? Again low. So what authors actually say is that these probabilities, these absolute numbers, they don't make sense. What actually makes sense is this ratio. So this is 8.9, this is 8.5 into 10 to the power minus 2, this is 1.36 and this is 0.96. What does it mean? See, everybody agrees that at least anecdotally, so probability of solid given ice, because ice is which state of water? Solid one. So probably they will occur in that window more often compared to gas. Okay. So you have this. Now what about water? What they say is both ice and steam, they are roughly equally related to water. So you are going to say the solid state of water is ice, the gaseous state of water is steam. So those kind of things. Okay. Now what do you understand from these ratios? And then we go. So what happened here? If you see this ratio, right? Ratio of solid given ice is high compared to, so this ratio of P of solid given ice divided by P of solid given steam, this one is higher. And similarly for steam, it is very low because you are dividing by that exact same thing. Okay. If you make this reverse, even this number will be higher, right? So this number will be close to this number if you take the reverse ratio. What about these two numbers? They are equally related, ratio is close to 1. They are equally unrelated, so ratio is close to 1. So what authors say is absolute probabilities, they don't give us much information. This is what we are going to use in our model from now onwards, and that is it for this class. You have a class at 11? Okay, so we don't have time to take questions, but if anybody has, you can talk to me offline, after the class.